suppose our line looks like this. Right, so this curve doesn't intersect. Actually, it should go all the way. Right. So still, it will make sense, right? Because from here I have this green line minus the black line. Here green line minus the black line. So everything is false and negative. But even the selection of negative number have a supremum. So basically, we will be end up at that difference is minimum somewhere around here. Okay. Right. So at this point, our supremum might attain be at somewhere around here. That's okay. And the nice thing about this conjugate function is convex even if my f is no. Would you like to prove it? Take a minute. Try to prove this by definition. Use that supremum property. So we are proving that f star is convex. And what are you going to use? You're going to use that supremum over theta h theta plus g theta will be less than equal to supremum of the individual supremums. Plus alright, let's begin. So what's your first thing to prove? So let's take 2 points. So we have to prove that f star theta x plus y. Let's start from the very beginning. So this is equal to the definition by very definition. That is nothing but. So let's y1 and let's type y1 and y2, okay? So y1 and y2. And that's by the very definition, that's nothing but supremum over all x. And that's theta y1 plus 1 minus theta y2 everything transpose minus f of x. Very good. Okay. And what we can do, we can distribute this transpose to the individual theta, right? So that is same as writing 2 primo over all x. Then I can write this as whole thing as theta y1 transpose x, and then I can do the standard thing. You break fx into theta fx and 1 minus theta fx. Correct? So it's minus fx. Right? So I pull this theta out from f. Right? Plus similar things. Then 1 minus theta y2 transpose x minus fx. Correct? Then you have, we're taking the supremum over of the sum of two functions, then we use that property. Then we get that this is nothing, that this is, let's make everything smaller. Right? And we know by the supremum property that this is less than equal to the individual supremum. Supremum over all x. And we can pull the theta out because theta is positive. y1 transpose x minus fx plus 1 minus theta times supremum over all x y2 transpose x minus fx. Correct? Right? And we know that that's nothing but nothing but f of y1, and that's nothing but f of y2. Correct? So you can use it by definition, prove that f star is convex, or you can just, if you remember some of the theorems of the last chapter, then we can straight away say that f star is convex because it is in the definition for each fixed value. If we're not taking the supremum for x fixed, this is an affine function because affine function in y, right? So for each fixed x, f star y is an affine function of y. So what is f star is doing? We're taking the supremum as point-wise supremum of collection of affine functions. So affine functions are convex, and we know from the last chapter there is a theorem that if we have a family of affine functions, then point-wise supremum is a convex function. Okay. So this can be also be said because f is f star is point-wise supremum of affine functions, hence convex. Let's do some concrete example of finding x star. So if f have a formula, then if f we can find some formula for x star, then we might be able to use it in our optimization problem. Because our eventual aim is to somehow push f star into the dual function, right? Because if you have an objective function, a given optimization problem, then we want to create a convex optimization problem in the dual form. So if the objective function plus the constraint has a nice expression for the dual function, then dual function can be easily pushed into optimization problem. We'll see an example of that. Alright, before that, let's very quickly find some quick example of f star. So fx is given by x times log of x. Domain is all the places where x is defined. Everything is real valued. The domain is also the real number. So we take the log. So log can only be taken for the positive number. So the domain is defined as only the positive half of the x. Alright. What we have to do is find a formula for f star. Alright, so let's start with the definition. What is f star y? F star y is, by definition, a supremum over all positive x's, right? Of what? Y transpose x, but as every y is a scalar, x is a scalar, so basically yx. Minus fx, and fx is x times log of x. Alright? So what do we have here? Now forget the left hand side f star y. Just keep your focus on from some fixed particular y, we are finding the supremum of this function. Okay? And we already know for each fixed y, wait. This is like a differentiable function. It's a smooth function. Okay? So if it's a smooth function, wherever it's a supremum or the infimum is attained, it's like a extremum point, so it's like a local minimum or a local maximum. Right? So the supremum of this expression for a fixed particular y can be simply attained. If it's the maximum, it's a critical point, then we can just find the derivative of this expression with respect to x of correct. So I understand that can be the maximum or that can be minimum. Then you just make some argument that the critical point corresponds to the minimum and not the maximum. Or sorry, the maximum and not the minimum. Right? So we just say, let's call this expression to be so we have to need to find a supremum of this for each fixed y, right?